logic gates and Boolean expressions. Alright, there's a competition on to name this chappie. That's the new icon. Alright, we are going to go from a logic gate to a Boolean expression first of all. So let's see what we start with. Firstly, we're going to imagine that there's a semiconductor gate circuit and it needs simplification. So we're going to use variables A, B, and C. Those are the input signals. And they're going to be assumed to be provided from switches, sensors, or perhaps some other circuit. But where these signals originate from is of no concern to the gate. All we've got to do is look at what we've got and do what's called gate reduction. Turn it into an expression and then simplify the actual gate. Remember the schematics. Take note that the little O at the end of the schematic represents the inverse. So that is a NAND because of that little O. That is a NOR because of that little circle. And that shape is a NOT anyway, but it has a circle. And we will look at E-NOR as well. Maybe not X-NOR. Maybe not. For AS anyway. Okay, the first step, you are given a gate, and remember that all gates are equivalent to Boolean addition, while AND gates are equivalent to Boolean multiplication. If you understand this, you'll know how to sequence the expression, or how to deal with the expression in the correct order. So if you were given a combination of multiplication and addition, multiplication must be done first. For example, look at this OR. Okay, if you imagine it as addition, it's 0, 1, 1, and 0. Remember, when we add Boolean 1 and 1, it actually results in a 0, carry 1. So if you remember that OR and addition are behave in the same way. And now let's look at multiply or AND. Now, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. Okay, that's a very handy tip that I haven't told you earlier that will help you understand the order later on and sequence of expressions. So here's our gate. We've got A, B, and C. I want you to take note that A and B feed into this shape here. If you go back up, you'll see that that shape is an AND. This is an OR, this is an AND, that's an OR, I beg your pardon, that's an AND, that's an OR, that's an AND, that's an AND, and that's an OR. And the output is Q. The reason why you need to know that is because later on you'll say Q is equal to, and then the Boolean expression that the gate results in. So A and B. So you're going to write the result on the output line, A and B, A dot B. I want you to break it up into levels. This is the first level of the gate, this is the second level of the gate, and this is the final level of the gate. Look at the connection. B also feeds into this AND, B feeds into this OR with C. And you'll notice that little loop there, that's a jump. So it's not connecting with that circuit at all. Step 2. Deal with the first level. So the result of this is A, B, or A dot B. Should be a dot there. The result of this one here is B feeds into it, and C feeds into it. So it's B and C. And this is B or C. B or C. That's our first level. So our helper, Mike, says work in levels. Take the first 3 and put the expression and work out the expression it should be. This is called writing the sub-expressions at the outputs of the first gates. These are sub-expressions on the output of the first gates. Okay. Step 3, the next Boolean expression. So we're looking at the next level. We've only got one gate in this level. The next level will take the first level expressions into account. This means we've got to look at the result hitting this particular schematic, which is AND. So what does that result in? Well, that's BC and then B or C. Notice the use of brackets. You say, when do we use brackets? You use them when it makes sense. B and C feed in from underneath, okay, and they are B dot C, and I would always put the multiplication one first anyway, and then B plus C is in brackets. Why do we put it in brackets? Because it is a separate input that is now part of this output. Okay, let's move on to the next stage. Oh, I've highlighted those because I just wanted to show you which ones make up which in this level of the expression. And I've highlighted the two types of connections. Well, that's a connection and that is not a connection. Alright? Step 4, the final expression. The final expression is Q, i.e. the total output, equals AB plus BC in brackets B plus C. We know that's A and B, or B and C, B or C. Okay? I'm using the plus and the multiply more freely now, so you can understand that they are related to the multiplication and addition of Booleans. And there it is clearly there. Q equals AB plus BC, B plus C. Q equals A and B, or B and C in brackets B or C. There's one more stage, and that's actually the simplification of this expression. You might be asked this in an exam to simplify that, and this is where we apply Boolean algebra theorem or Boolean algebra rules. If you look at AB or BC, B or C, and we call that distributing the terms, so it becomes AB or BBC or BCC. So how does that work? Well, when you have brackets in algebra, you've got to join the algebraic expression outside the bracket with those inside the bracket. That's why you end up with BCC, because you've joined BC to that C, BCC. And the B and the B join with the C here. That just stays the same. Let's simplify that. We know that BBC is BC. Well, in algebraic terms, a B, 1B times 1B is just simply B, or 1B, if you like to imagine a 1 in front of it. C obviously is singular, and likewise the CC becomes a C. We call that applying identity if you want to know the term, but I don't think you need to know the term in AS computing. So the A plus the A equals A. This is to the second and third terms. Now we end up with AB or BC. Factoring B out of terms, this is great because now B is the common factor. We can put outside the bracket and put AC in the bracket. So it's B in brackets A or C. That's our simplest form. Simplest means finding the fewest gates to implement. And we can turn this back into a gate. So what ended up, or started out as being a very complex gate, can actually be reduced. It's called reducing the expression, and reduced into a gate. This is it. Okay? So draw gates for each step. Well, this is the start of it. So this is step 1. And he says, evaluate the expression following proper mathematical order of operations, multiplication before addition, operations inside parentheses before anything else. Remember again that the OR gates are equivalent to addition and multiplication. So this is like saying A plus C. This is step 2. Alright, and now we've ended up with Q equals B, A or C. Remember? That was our simplest expression. Q equals B, A plus C, or B and A plus C. And now we can draw the gate. So this gate consists of one OR schematic and one AND schematic. A and C feeding into this one that B feeds into, the AND. Alright, so you might be asked to go full circle. And what I mean by full circle, we were given, let's just go right up to the very beginning. We were given the gate, we turned it into an expression, we simplified the expression, and then we drew another gate for it. So this gate is actually equivalent to that. It's quite amazing. And we now can turn the whole gate thing into a gate exercise or truth table. So this gate, all right, A and B, results in what output? This gate, A and B, sorry, A nor B, results in what output, and so on and so forth. This is a little exercise that I want you to do, especially because you're missing this particular lesson on Friday. You're on a study seminar. So this is the exercise I want you to do. Could you pause at this stage and mentally just, or jot this down on a piece of paper and see what your results are? I'll allow you time to pause, jot it down, and in the very next slide we'll give you the answers. Alright, there we go. There's our AND, but it's the inverse, so it's NAND. So why is it 1 when we say 0, 0? 0 and 0 should really be 0. But because of the little inversion, we've got to invert the results. Okay, so I hope you got that all right. It's fairly straightforward, and this is an excellent exercise. You will get at least one of these in the exam. I reckon, looking at the past exams, you're probably going to get either that one, or they'd like to throw, probably not or not. Try remembering what that one's all about, and that one, just in case they throw a complicated one at you. But if you can remember the simplest ones, the NAND, NOR, AND, XNOR, OR, NOT, those are the main ones. Okay, try to learn those off pat, be able to sketch them in your mind or down on a piece of paper. We're going to look at something called DeMorgans Laws. DeMorgans Laws, what he did, this chappie, De Morgan, I think that's him, we might call him De Morgan, but the competition is to come up with a name for this chap. He's Mike. This chappie here, x plus y plus z, or x or y or z, we know that De Morgan invented this inversion bar. It means to invert it, and this is exactly the same as saying, and please note, annotation of a little apostrophe means the bar. If ever you see that little apostrophe, it means it takes a bar, the whole thing takes a bar. That one there next to the letter means the letter takes the bar. This, x or y or z, inverted, means exactly the same as inverted x and inverted y and inverted z. Alright? This is an important law to remember, because if you ever see that, you know the expression actually means that. And then you can work out a truth table from that. Alright, let's look at this law. The whole expression, x and y and z inverted, equals inverted x or inverted y or inverted z. Very important, because recently we were given an exercise and we all went to great pains to work that out, whereas what we should have done first of all is turned it, which is what De Morgan wanted us to do, to turn it into the converse or antithesis expression, I beg your pardon, the antitheses. So this P and Q is exactly the same as P inverted or Q inverted, or I prefer to say inverted P or inverted Q. And this P or Q inverted is exactly the same as inverted P and inverted Q. Okay, makes it a hang of a lot easier, and we would have come up with similar results, or exactly the same results, doing it the painstaking way. But if we had first of all used the De Morgan law, we would have found the process of creating a truth table and the output a lot simpler. That's referring to the Boolean expression worksheet from Caboodle that we were all trying on the Monday. So not P and Q is the same as saying not P or not Q. And not P or Q is the same as saying not P and not Q either. Who's that? Okay, never mind. And that's the end of that. I hope that was understandable. And please let me know how that exercise on the third to last slide went.